Hi, thanks for attending this virtual conference. My colleague Jiewen and I are going to talk about enabling Rust for UEFI firmware. So since we're not here in person, we thought we would share at least a little bit of information about ourselves and our pictures. So Jiewen is a principal engineer at Intel who's been doing firmware for the last 15 years and driving a lot of efforts in the open and the industry groups such as the UEFI forum and the Trusted Computing Group. Myself, I'm Vincent Zimmer. I'm also with Intel. I've been doing firmware for a little bit of time also, and I lead some of the UEFI efforts in this space, including the UEFI security subteam. But beyond our biographies and our glamorous pictures, what we want to talk about is providing a landscape of EDK2 security, and then delve into the Rust language and specifically enabling Rust for EDK2. So to provide some background and motivation for this effort, I'm going to talk a little bit about EDK2, provide a security summary. In the space of security issues, there's broad classes of software from applications, hypervisors, and underlying firmware. And so what we're talking about here is EDK2 style firmware and breaking up our analysis into both the open and closed source. So open source EDK2, such you'd find on tinocore.org, when we went through some of the public advisories, we observed about half of the issues are buffer overflow and integer overflow. A slightly smaller amount was observed in our closed source, and then the other concentration of issues are more semantic bugs, whether it's in system management mode, variables, or applying locks. And you'll notice that as the open source EDK2 code is more algorithmically intensive software layers, has more issues, whereas the closed source, more silicon intensive, has less buffer overflows and more issues like register locking and other things that impact hardware. These numbers are similar to what you'd find, like what Microsoft MSRC has published, where they see about 70% of their issues are buffer overflows. But for each case, those classes of software issues and firmware issues are the same. We're really writing in an imperative language like C, where we have buffer overflow, integer overflows, and uninitialized variables. The initial buffer overflow was in Multics operating system in the 60s, and they're still prevailing today. Just as firmware and software are very similar, software mitigations can also be used for firmware. I'm going to talk about some of the examples of these mitigations. Specifically, there's really three ways to provide prevention. You can eliminate the vulnerability, you can break or prevent the exploit from happening, and then when the exploit happens, contain it. And to that end, with respect to eliminating vulnerabilities, one of the best is reducing the attack surface. Having fewer code objects that are exposed to the potential attack. The SMI handler profile feature is one way to remove SMM drivers, for example. As when Windows Snyder said, the best defense for a software engineer is the delete key, removing code, removing features. But a lot of features need to be there, and so the next way to eliminate vulnerabilities is analyzing the code you have to deploy. So you have static analysis, memory sanitizers, and of course, there's also testing and fuzzing, positive and negative testing to see if your code actually exhibits any issues, and then vulnerability scanning like chipsec. Are all the lock bits set, or are there some other assets that aren't programmed appropriately? That's in the elimination space. The next is, break your exploit. So assume the exploit gets in, but prevent it from affecting the attack. And that's where things like a stack card, which is something in compilers today where you have canaries or some object on the stack that if there is an overflow, there's a runtime check. Address space randomization is another where, if an attack is trying to target a known layout of memory, if you shuffle some of the content, say where your DXC core or some of your SMM drivers are, you can't write. It makes it difficult to write an attack that works on a broad class of systems. And then non-executable data. So an example is the SMM memory protection, where have your data allocations something that if an attacker gains control, he can't execute. And then emergent capabilities, whether it's hardware or software, for things like control flow. And control flow enforcement technology in the recent 11th generation Intel CPUs is one example of a hardware way to break an exploit. And then finally, code integrity. Very common example of that is UEFI secure boot, i.e. don't run code that hasn't been signed by a known entity. So again, eliminate the exploit, break the exploit, and then finally, assuming the exploit gets in, providing, ensuring that it can't do too much damage. So there's a lot of techniques used today in higher level software, jailing software, deprivileging it, sandboxing. If you were to run in the EFI bytecode, you could sandbox the said EBC bytecodes with some software inline reference monitor, some software isolation, or push some code to ring 3, or maybe use things like virtualization technology to deprivilege code, so that if there is attack code, say it gets past EFI secure boot, it bypasses one of your exploit protections, ensure that it can't do any damage to your system. So eliminate a vulnerability, catch it, and if it gets in, potentially contain it. So these are sort of 3 classes of prevention. Many can be seen in the open source, some are emergent research areas. But is that enough? So instead of just providing the guidance we had in the previous chart, what about correct by construction, or preventing the developer from actually introducing the flaws in the first place? And that's where exploring things like a type-safe language or language-based security we see as a complement to the other techniques. It isn't a silver bullet, but catch these common class of issues like integer overflow and others through the use of a type-safe language. And to that end, one language that is gaining a lot of interest in the community for system software, such as host firmware, is Rust. And to explore Rust a little more, I'm going to welcome my colleague Jiewen to give an overview of the language, and then click down into how we may use Rust with EDK2 based firmware.
Okay, thank you for Vincent. Now let me have a brief introduction for the Rust language. Then we move to how to enable Rust for EDK2. Rust is a new system programming language. It was designed by Mozilla Grandin Hall. Release was at 2014. The most attractive attribute of Rust is the reliability. It has rich type system and the ownership model that can guarantee the memory safety and the thread safety. The system programming language is used to write the operating system and device driver. The C language is the most popular one. However, C is also notorious for the memory safety. For a long time, it is hard to write a secure code with C. For example, we know the buffer overflow for more than 13 years since the Morris swarm, but today we still see the buffer overflow issues in the firmware. Rust is not the only type-safe language. Comparing with others is very fast and memory efficient because the memory issues are eliminated at compiler time instead of runtime. Unlike unlike Java, Rust does not have the garbage collection. As such, it can provide the performance-critical services and run on an embedded device. Rust uses a different way to resolve different problems. For buffer overflow, the best way is to load the object and refer it based upon the defined data structure. Out-of-boundary access can be detected at compile time. However, the reality is that we might also need to use offset or index to refer a slice for the complicated data structure. Rust compiler injects code to do some runtime boundary check. If the out-of-boundary access is detected, the code calls a panic handler. The panic handler can be implemented as a dead loop, similar to the exception handler. Heap management issue, such as USF-free or double-free, can be managed by the Rust ownership model. The violation can be detected at compile time, and the uninitialized variable is automatically eliminated because Rust explicit requires the initialization. No pointer dereference is an interesting question. The inventor Tony Hall treated no pointer as a $1 million mistake. It was invented in 1965 just because it's easy to implement. Eventually, it has led to numerous errors, vulnerabilities, and system crashes. If the data might be no value, you can use the option T in new, and the program can use some T pattern to get the data and use a null pattern to handle the no value case. The null pointer dereference may happen in memory allocation failure. Just use the alloc arrow for the allocate check at runtime. If we believe that the memory allocation should always be success, then we can use the dead loop in the alloc arrow handler. Besides memory safety, the arithmetic arrow contributes to a large portion of root cause of overflow, such as integer overflow on addition or multiplications. Some famous BIOS issues, such as BMP overflow in 2009, was caused by multiplication overflow. The UEFI capsule coalesce issue in 2014 was also caused by addition overflow. Rust provides a flexible way to handle that. It defines a set of functions such as checked add, overflowing add, saturation add, and wrapping add. It defines the compiler flag on overflow checks for the direct operation. The runtime check will run into a panic handler if the runtime overflow check failures. If the compiler flag is not used, the debug build will generate a checked code, while the release version just discards the overflow data. The Rust checked version function is similar to the save int lib in EDK2. The developer chooses the right version to parse the external input. Typecasting is another risk. Rust always requires explicit typecasting at compile time. This is a brief introduction for Rust. Now we can see how to build the Rust in EDK2. We create the EDK2 Rust branch in EDK2 staging repository. And we also update the EDK2 Rust branch in a personal Git repository with the latest update. We plan to sync to the staging periodically. We built the EFI Rust module with Rust Cargo X build in Windows or Linux environment. In order to generate .EFI image directly, we need to use the x86-64 unknown EFI target or i686 unknown UEFI. Both of them are available in the Rustlang Git master. These targets are also used to generate the PE library in Windows or Linux. To build the Rust library and the C library together, we can use LLVM 9.0 compiler, which is also supported in current EDK2. EDK2 base tool is updated to support different build type. You can indicate a .rs file in INF, and you can create a cargo.toml file and add to INF. Below example shows that we add a cargo.toml in a base BMP support lib rust.inf, and in cargo.toml we describe the Rust uh, the files. It can build to a base BMP support lib Rust directly. Of course, we can link a Rust library with C driver, or we can link a C library with a Rust module. It's very flexible. This figure shows the EDK2 Rust build process. We can describe a TOML file in INF in EDK2 build tool, and the TOML file can describe the Rust file. And the EDK2 build rule will get the TOML from INF and invoke the Rust X build system to process the Rust TOML. The X build generate the .EFI directly, or it can generate a Rust library. Then ARVM linker can link the Rust library and with C library into a final .EFI image. Because EFI is not an OS environment, not all Rust libraries can be used. In current design, we can only use core or crate. This is a function of Rust. Need to implement a panic handler for the runtime check because the compiler will inject those handler reference. We may use alloc crate for advanced data structure such as box or vector. To use that, we need to implement a global allocator. And into the allocate or deallocate can be mapped to UEFI allocate pool and a free pool. To handle the memory allocation failure, we also need to implement alloc error handler. The STD crate includes lots of advanced features such as file system access and network access, which is not well supported. In EDK2, we create some basic examples. For example, the FAT-Rust is a simple read-only FAT file system library. You can read the OS loader from the EFI system partition and boot to it. A Rust version EFI lib provide the memory allocation, debug log, and the UEFI boot services, etc. The Rust language can only support UTF-8 style native string, but the EFI requires a char16 string. As such, we create a EFI string crate to handle char16 string for EFI to help the developer write Unicode string easily. Recently, we worked on a Rust-based SAC as the initial program loader. It can be used to load the Rust-based payload, such as Rust hypervisor firmware or Rust-based EFI payload. But that is in progress. We are working on that. We also did research for the pure Rust version crypto library. Rust TLS is a modern TLS library with Rust. It uses Ring for cryptography and WebPKI for certificate verification. So we tried to enable Ring and WebKPI in a EFI bare metal environment as a Rust version crypto library. However, they do not support EFI target very well. As such, we add EFI target OS in the code. One thing we noticed that Ring WebKPI use the C standard lab RAND. In EDK2, we don't have standard lib rand function. As such, we created the EFI random crate who use a read random and read seed instruction to link with Ring or WebPKI or crypto library to support the random services. Rust language can guarantee the memory safety. However, there are some limitations for using Rust in the EFI development. First, the EFI specification and the interface, such as EFI boot services protocols, are defined in C language. Currently, EDK2 has been called or based upon the C language. We may convert part of the module into Rust, but it's hard to convert all modules into Rust at one time. Cross-module interaction still requires C API. As such, the unsafe code is unavoidable. Here we want to summarize where the Rust can help in the EFI EDK2 project. First, to eliminate the vulnerability, by using the compiler time check, we can eliminate the uninitialized variable. The use after free or double free can be avoided with ownership model. Second, break the exploitation. Rust can help generate a runtime check for memory boundary check or integrity overflow check. In case the developer cannot write code correctly, this violation can be caught at runtime and it can cause a dead loop. To avoid dead loop, the developer needs to write correct boundary check code or use proper integer operation functions. However, we also notice that some security vulnerabilities that the Rust language cannot help. For example, the silicon register lock. Rust language cannot understand the silicon register lock attribute. We need to use a chipset tool to check if all required register lock properly. Security policy means to enable or disable secure features such as EFI secure boot or 4K aligned runtime module in UEFI memory attribute table. It is not related to Rust language. We need a policy checker. TOC/TOU attack prevents in the S7 handler is a software pattern. We need to copy S7 common buffer into SRAM and process it. We also need to rendezvous all APs in SMM before the SMI handler unlock a critical register. Those are also out of language perspective. A careful secure design is required. SMN callout is required hardware restrictions such as SMN code access MSR or non-executable in SMN page table. The last thing is unsafe code block in Rust for C interaction. The unsafe block always need careful code review. Please aware that putting some code in Rust unsafe block does not help from security perspective. Recently, we rethink how to integrate Rust in the firmware. We notice that there are multiple projects on Rust-based firmware, such as Allboot, that is a C boot without written in Rust, and there's a Rust hypervisor firmware. Also, there are a different C-based firmware project besides EDK2, such as Coreboot, Slim Bootloader, and Universal Payload, etc. A trend is to separate firmware into two parts, the bootloader and the payload. The bootloader is to initialize the silicon, while a payload is to provide necessary services and interface to operating system. An example of bootloader is Coreboot or Slim Bootloader, while the payload example is the UEFI payload or U-boot, etc. Some projects, such as EDK2 firmware, is a combination, including both bootloader and the payload. With that, we can imagine that Rust-based firmware could be those two types as well. Rust-based IPL as a bootloader, and the Rust-based UEFI payload can be a generic payload. It could be UEFI or it could be something else. Recently, we are investigating the Rust-based IPL initial program loader, a SEC implementation with Rust. It may interactive with Intel FSP to initialize the silicon. Once that is done, it can boot a Rust-based payload. With that solution, we can only see the reset vector has some assembly code, but the rest should be written in Rust. The Rust IPL as a bootloader and the Rust payload. It may boot to a Rust operating system. The Rust IPL is still working progress, and we're looking for feedback on that direction. And here is a link we referred in this talk. Is we have did the UEFI Rust overview before, and you can see the secure bug and the Rust type safe language. And here's a link for other Rust-related projects such as Rust Hypervisor Firmware, Allboot, Rust OSDV, Talk OS, Open Titan, etc. To learn more about EFI security, Vincent and I have written a book, Building Secure Firmware. We share our knowledge and thought on a different aspect of firmware security. And there's one chapter talk about the language used in the firmware, including Rust. I provide the link in Amazon or Spring so people can buy it or download. So that is all for our talk, and we'll pause to see if you have any questions.